All right, this is our last video on trigonometric substitution. So in part one, we looked at integrals involving the square root of a squared minus x squared. And the trig substitution we wanted to use was x equals a sine of theta. In part two, we looked at integrals that had a square root of x squared plus a squared. And the substitution we wanted to use there was x equals a tangent of theta. Here we're going to be looking at integrals involving the square root of x squared minus a squared. And here we're going to be wanting to use x equals a secant of theta. So we're going to work out kind of what it looks like a little bit generically, and then we'll do a more concrete example. So we're going to go ahead and integrate the integral of square root of x squared minus a squared dx. So we're going to let x equal a secant of theta. Dx is going to be a secant of theta, tangent of theta, d theta. So we have the square root of a secant of theta squared minus a squared. Dx is a secant of theta, tangent of theta, d theta. Slide out the a, factor out an a squared. So the a from the a secant theta, tangent theta, d theta. And then the a squared from the a secant of theta quantity squared minus a squared. So that's going to be out of the radical there. We have the radical a squared times secant squared theta minus 1. And then times secant of theta, tangent of theta, d theta. Okay, so secant squared of theta is going to be equal to, well, secant squared is equal to tangent squared plus 1. So secant squared minus 1 is equal to tangent squared. So I'm going to make that replacement under the radical, and then secant theta, tangent theta, d theta. And so we're going to be taking the square root of tangent squares. We've got to be careful about where the theta is. Okay, so I think with our book we are using the restricted domain for the secant as 0 to pi over 2, not including pi over 2, and then pi over 2 to pi, again not including pi over 2. That's the restricted domain. So the tangent is going to be positive in quadrant 1, but it will be negative in quadrant 2. So that's going to affect how the square root of tangent squared is going to look. Okay. So it's going to be equal to the absolute value of tangent, and it's going to be equal to negative tangent of theta if theta is in quadrant 2, and it's going to be equal to positive tangent if theta is in quadrant 1. Okay, so typically how we're going to use this in our examples is we'll just assume that we're in quadrant 1, so the square root of the tangent squared will just be the tangent. If you're doing an indefinite integral where you're getting into quadrant 2, then sure you would use the negative tangent variety here. And then it doesn't make too much difference in the integral here, where you're just going to have one's going to end up being a negative and the other's going to be a positive of each other for this indefinite case. So we're going to go ahead and operate under our thetas between 0 and pi over 2. So this gives us a integral of a tangent of theta, secant of theta times the tangent of theta d theta, which is going to be a squared, integral of tangent squared theta, secant theta d theta. And so this is a trigonometric integral. If we got secants and tangents, we wanted to save a secant squared and convert everything to tangents because the derivative of tangent is secant squared. Or we wanted to save a secant tangent and convert everything to secants. Either one of those is not going to work out real well, but we are going to rewrite the tangent squared as secant squared theta minus 1. Times the secant of theta. And this actually becomes integrals that we do know. So this is going to be a squared, integral of secant cubed theta. So in the previous video I looked up this particular integral, integral of secant cubed, that is derived it's in the textbook, and it's also in the 3.2 video part 2. Okay, minus the integral of the secant of theta d theta. Okay, and the integral of secant of theta, that was something we did in calculus 1. And the integral of secant of theta is the natural log absolute value of secant of theta plus tangent of theta, and then plus your constant of integration. So this is going to be a squared, and then the secant cubed is going to be secant of theta, tangent of theta, plus natural log absolute value of secant of theta, tangent of theta, all over 2. And then the secant integral is natural log absolute value of secant of theta plus the tangent of theta, and then plus c. Okay, so this is going to be a squared over 2, so we're going to slide out the 2. And so we'll have secant of theta, tangent of theta, minus the natural log of the absolute value of the secant of theta plus the tangent of theta, and then plus c. We'll draw our reference triangle, and again, we're just going to assume that we're in quadrant 1. Here's a right angle into theta. And we have x is equal to a secant of theta, so secant of theta is equal to x over a. And so that gives us the hypotenuse and the adjacent side. Using the Pythagorean theorem, the opposite side is going to be the square root of x squared minus a squared. So we need to fill in for the secant and the tangent. So we got secant tangent of theta is going to be the square root of x squared minus a squared all over a. So we're going to make those substitutions. So we're going to have a squared over 2. And then secant times tangent, so x times the square root of x squared minus a squared, all over a times a, which is a squared, minus the natural log of the absolute value of x plus the square root of x squared minus a squared, all over a, so they had a common denominator there. That should be an a, not a 2. That should be an a. Okay. And plus constant of integration, all right? And so that's our ni derivative. Again, if you might look this up as an integral table, it is possible that this a in the denominator is not there. Properties of logarithms are used to make that go away. It doesn't really go away, it just gets gobbled up by the constant of integration. Okay. Now, if you were operating under the negative tangent, we just stick a negative in front of our integrand here. Okay, and that's it. All right, let's go ahead and look at an example where we're going to use the substitution x equals a secant of theta. So we're going to look at the integral of 23 square root of x squared minus 25. So that's our q right there, square root of x squared minus a squared. That is going to be secant x equals a secant as our substitution. All over x to the 4th dx. So we're going to go ahead and let x equal a secant of theta, which is going to be 5 secant of theta. Differential dx is going to be 5 secant of theta, tangent of theta, d theta. We'll go ahead and draw in our reference triangle here. Here's our theta, and we have the secant of theta is going to be x over 5. So that gives us the hypotenuse and the adjacent side. Using the Pythagorean theorem, we're going to have the opposite side is the square root of x squared minus 25. Okay, so the tangent of theta is equal to the square root of x squared minus 25 all over 5. Okay, multiply both sides by 5, and we have 5 tangent of theta is equal to the square root of x squared minus 25. Alrighty, so let's go ahead and slide the 23 out. Integral of 5 tangents of theta replaces the radical. dx is 5 secant theta, tangent theta, d theta. And then x to the 4th is going to be 5 secant of theta to the 4th power. Alright, so we have 5 times 5 in the numerator, and we have 5 to the 4th in the denominator, so we still have a 5 squared in the denominator. We're going to go ahead and slide that out, so 23 over 25. Integral of secant of theta, tangent squared of theta, all over secant to the 4th theta d theta. So 23 over 25. Integral of tangent squared theta over secant cubed theta d theta. And we'll go ahead and rewrite the tangent squared and the secant cubed as the sine squared over the cosine squared divided by 1 over the cosine cubed of theta d theta. d theta. So we have 23 over 25 sine squared theta over cosine squared theta times cosine cubed theta over 1 d theta. So this is going to give us 23 over 25 integral of sine squared theta cosine theta d theta. So this is a nice easy u substitution problem. U is the sine of theta, du is the cosine of theta d theta. So it's going to be 23 over 25, integral of u squared du. So 23 over 25 times u to the third over 3 plus constant of integration. So 23 over 75 sine to the third theta plus c. We'll go over to our reference triangle and grab the sine. The sine of theta is equal to the opposite, square root of x squared minus 25 over the hypotenuse of x. 23 over 75 is equal to the square root of x squared minus 25 over x cubed plus c. So it's going to be 23 over 75, x squared minus 25 to the 3/2 power all over x cubed, and then plus constant of integration. Okay, and so that is what trig substitution is going to be like. Some may be more complicated than others, but once you get the trig substitution part done, everything is in terms of theta, then it becomes a trigonometric integral, so it becomes something that we would have seen in section 3.2. Alrighty, well, we'll see you next time.